Welcome to Brain Vision.
Hey everyone, this is question number 25 from chapter 21. In this problem, we're given a proton that is traveling horizontally to the right at 4.5 times 10 to the 6 meters per second. We're asked to find the magnitude and direction of the weakest electric field that can bring the proton to rest. We're asked to find the time it takes for the proton to stop, and then we're asked to find the minimum field magnitude and direction needed to stop an electron. So I sketched this out. This is the proton. It's moving to the right. So for part A here, magnitude and direction of the weakest electric field that can bring the proton to rest. If we're looking at a proton moving to the right, it's going to have to stop. It's going to have to decelerate and stop moving, and that means the electric field is going to have to point to the left. So we can go ahead and establish that before we even do any math. But let's move on to the math here. We have a distance and we have a speed. So we have distance, we have velocity, we have a final velocity of 0. But in order to find an electric field, we need some more information, because the equations that we have for electric fields are F equals EQ, and we know that F equals MA. So we know mass of a proton, but we don't have A here, and we know charge, and we need to find this electric field. So what we need to find first is A, and we can actually do that with kinematics, throwing it back a little bit. So we have a kinematic equation that relates velocity and distance, and that is v squared equals v naught squared plus 2AD. So we have our V naught, our VF obviously is 0 because we're coming to a stop, and we have our distance. So we can rearrange this equation and solve for A. And we get A equals, we subtract V naught over to the other side, so minus V naught squared over 2D, which is our distance, and we're given that in the problem. So now we can go ahead and plug in and solve for everything. So our V naught is minus 4.5. That's squared. And we divide that by 2. And our distance here, which is, let's see, 33.2 centimeters. So we have to move that over, and we get 0.032 meters. And that's going to give us an acceleration of minus 3.164 times 10 to the 14th. Meters per second squared. So that's our acceleration. And now we look back up at these equations that I wrote, F equals EQ. We can rearrange, we're looking for electric field, we can rearrange and do E equals F over Q. And we know that F equals MA, so it equals MA over Q. We just solved for all of this, so we can go ahead and plug it in. So mass of a proton, mass of proton, 1.673 times 10 to the minus 27th kilograms. Then our acceleration, we just solved, minus 3.164. times 10 to the 14th meters per second squared. And then we have charge of a proton, which is 1.6 times 10 to the minus 19th. Coulombs. And that's going to give us an electric field equal to minus 3.3, so minus being the to the left, so 3.3 is our magnitude. Times 10 to the 6th newtons per coulombs, and that is to the left. So that's our answer to part B, or part A, excuse me. Part B now is asking how long it takes the proton to stop, and that is a pretty easy kinematic equation again, because we just found acceleration, and we have initial velocity and final velocity. So V here, we're going to use our trusty V equals V naught plus AT. And our V is 0, and we can solve for T. T equals minus V naught over A. Plug in our numbers. Minus 4.5 times 10 to the 6th. Our acceleration, just solve for. Minus 3.164 times 10 to the 14th. And that gives us a time of 14.6 nanoseconds. So 14.6, that's our answer for part B. And now we move on to part C, which is asking for the strength of the electric field if the electron, or if the proton was replaced by an electron. So when we're looking at this, it's the same process that we just used, but we don't need to solve for acceleration. It's going to be the same. So we know our acceleration is minus 3.164, and we just go back to E equals F over Q, and that's going to be MA over Q. We have everything. Our mass is what's changing here, and we can go ahead and solve for the electric field. So we have mass 9.2, mass of an electron 9.202 times 10 times 10 to the minus 31st kilograms. Our acceleration minus 3.164 times 10 to the 14th meters per second squared. And then our Q for an electron is negative 1.6 times 10 to the minus 19th coulombs. And that is going to give us 1.8 times 10 to the 3rd newtons per coulombs. And this is positive, so it is in the right direction, same direction as the electron is moving.